second paper, second paper, finite element analysis of a vehicle chassis cross member sport weld design. Authors are RMRC, Udayanandana, PPSS, Pussepitiya and Lahr. I invite Udayanandana to Mr. Udayanandana is the presenting author. He is currently working as a lecturer at Advanced Technological Institute, Colombo, and he holds 2 postgraduate diploma, one from Manufacturing System Engineering, University of Morocco, and Mechanical Engineering from Birmingham City University, UK. So it's so to you.
Thank you, sir. Good afternoon, ladies and gentlemen. We are going to present about the finite engine analysis of vehicle chassis cross member design and how to optimize the wheel pattern. This is the content I am going to present today. Introduction and method I use to validate the set and validation, the result, and finally conclude. Actually, if we consider the sheet metal industry, this is spot welding is wide use method for producing these parts, especially in mass production in automobile industry. And if we use optimization of the number and location of spot welding with major consideration, economic consideration, because in mass production, if you could reduce the single spot weld, it's a huge cost saving, the production process. So I did the experiment test, consider the chassis cross member. This is the experiment that is conducted. So you can see there, I use the, here is the dial indicator and the loads applied, and the is the strain gauges I use, 2 strain gauges at top, one is strain gauge at top and other one is at the bottom. These are the strain gauge value readers. After that, I applied several loads on the holder there. Then measure the deflection and strain value. This is the result. Observation result. Applied weight and relevant deflection and strain at top and bottom. So then I conducted the theoretical calculation of this chassis cross member. So mainly these are the data. For one load we did the calculation. Load applied is 101.2 kilogram, and thickness measured is 1.22 millimeters. So these are the data. These are the results I could calculate from the theoretical calculation. Then third one is finite element modeling. It's a modeling analysis software, and I could model the spot weld positions. Under the observation, we could measure the position of current chassis cross member. So these are the distance between these weld positions. They are not, there's no much pattern there. So this randomly spot welded chassis cross member. And in analysis of finite element model, these are the boundary conditions applied. So I applied the 2 loads, A and B positions. They are the position attached to the vehicle, and C and D, here C and D, so they are a remote displacement. That means it has freedom to move in Z direction and rotate about X axis. And finite element, after several refinement, this is the mesh model generator, and the results got. This is the result for the elastic strain at bottom surface. And the different refinements and relevant data obtained after in the finite element analysis. So gradually reduce the element size of the mesh modeling, and relevant results obtained, strain and deflection. So next, I consider the convergence of this deflection. So after that, you can accept the result of that finite element model, because there is a convergence of the result. When you compare the results obtained, strain at the top, experimental value, and the theoretical values. After that, this is the experimental value, theoretical value, and finite element values for the strain at top, strain at bottom, and deflection. So you can see they are almost same in theoretical, but some deviation from in experimental. So, and when you look at so the conversion is achieved because there is a 2.1% deviation in this previous result. So that is in acceptable range, so that I accepted that value. After that, new design was proposed. This actually the highest stress area is this middle part. So that area, number of weld point is increased, and again analysis was conducted. From that, we could reduce one weld point, and the strength could be increased. These are the results existing and proposed design. Same load applied, and number of weld point is reduced, and stress maximum stress is much, so proposed design is reduced, and buckling load also considered. The capacity of the new design is increased. So, as a conclusion, I could say that this finite element successful linear elastic finite element model was developed to obtain prediction of stresses, deflection and strain, and it was validated by considering the convergence of experimental and theoretical results, and the proposed pattern where we could reduce the number of weld points, and the strength also increase.
Any questions from audience?
Can you go back to that one where you came from 27 to 26? No, dialogue. The dialogue. Right. Now, originally the points were equidistant,
No.
the weld point?
No.
No, what is the difference between the number I can understand,
Yeah.
27 became 26, but what about the positioning of that? Was it originally equal distances or?
They are randomly welded.
Original?
Yes, original.
Right. So it's not the, it's because you are doing it in a more systematic manner that you have got your stresses low.
Yes, because I considered the more high stress area.
Yes,
That area I put more.
And less in other
other
areas.
areas.
Does it depend on how good your spot weld is?
That also.
So how do you, now in practice, in theory you assume a certain strength. In practice, some of the spot welds I've seen in things that are made, they just come out.
Yeah. That was
So how do you ensure that when you do a design and you are very critical about the number, then the quality of the weld is also important.
That was important.
Is there a method to check that?
As a improvement, actually, we have to do that experimentally welded it and then test it again.
No, I'm asking on site, how, if there are methods of checking whether the weld is good or bad, do you do anything like that? Or do they just sort of,
Microscopic analysis or X-ray, that kind of
on site?
Have you done any work? Yeah.
strength checking. No, one by one I check.
Weld quality check.
Weld quality check.
Have you checked weld quality?
Separately I will check. That is, you just check the applied load and then
No, can you do that on site? No, X-ray measurements I don't think can be on site.
there is non-destructive basis.
I don't know.
Like X-ray or microscope studies.
Any more questions from audience? Here, what your last paper, total load required to buckle. How do you know that buckle or after bending? How do you know buckle? You have calculated buckle.
Yes.
How do you know that buckle or that's problem by bending?
They are twisting loads are applied. That's
How can we apply twisting load there? Decimeters. How many members for one decim? Only one member. How do you know that applied force for the buckle or bending?
first consider the bending. And there are any buckling load that
What is the exact difference between buckling load and bending? You got chassis and apply load. It is going to bend or buckle.
the bend.
Here your table you show.
In actual dynamic motion, it can be.
How can you buckle?
No, when you are using the, you have to be
Yeah,
careful,
careful, yeah.
because bending and non-bending, buckling has a different meaning.
Yeah. Twisting motion.
So, other thing I would know, you have an application specific. Your spot weld length not equal. You put random. Okay. Your research should be generic. Okay. This technique we can apply for other places as well. Because you have designed only specific to your this beam. You have to derive a formula. What is the weld length? Like spot weld vary with weld diameter. Okay. If you get larger spot weld matching, you get larger diameter, then higher strength. Then this is not applicable for that kind of work. I think you have find further analysis. Then as you got your research. Any more questions? Okay, thank you.